In this last lesson, we're going to still continue to talk about volumes of revolution, but we're going to talk about a new method called cylindrical shells. Now, we can use this method on the same kinds of solids as we did the disk method and the washer method. The difference is that with the disk and the washer method, when we integrate with respect to x, we rotate it around the x-axis. And when we integrate with respect to y, it's because we're rotating it around the y-axis. With cylindrical shells, we're going to integrate with respect to x when we rotate around the y-axis. And when we integrate with respect to y, we're going to rotate around the x-axis. So let's take a look at this first picture. Just like before, we defined a region R that's bounded above by a graph of the function f of x, that's in orange, below by the x-axis, and then we're going to do this on an interval from a to b. Then we revolve the region around the y-axis. That's in the second picture. So here's the region that we're revolving. This is our R, and then we revolve it around the y-axis in the second picture. And this is different from what we've done before because previously we've taken those regions and if we've defined them in terms of x, then we revolve them around the x-axis. So with cylindrical shells, we're defining everything in terms of x, but we're rotating around the y-axis. Then if you look at this next set of pictures, A, B, and C, just like before, we're going to partition the interval into equal pieces using regular lengths and widths and all that. We're going to break it up into cylindrical shells. So we have all of these shells in here, like interlocking to create this solid. Here's one shell by itself, so you can imagine what it looks like. And then you can see what the width of the shell looks like. When we spin it around the y-axis, that's a cross section, and that's going to be our width, delta x. Now, if you imagine that we cut one of these cylindrical shells and we unwrap it, what we're going to get is a rectangular prism. And the rectangular prism is going to have a width of delta x. And we want that delta x to get smaller and smaller and smaller so we can get more and more and more cylindrical shells inside that solid so that we can get the most accurate volume. Now, if you imagine how we're going to find the volume of that rectangular prism, if you look at, let's see, I'll do this in red. If you look at the top of that cylindrical shell, when we unwrap it, that's this part right here. Now, the top of that cylindrical shell is a circle. It's the circumference of a circle. And the circumference of a circle, that formula is 2 pi r. Now, the radius of this circle, if we come out, I'll do this in purple, if we come out from the x-axis, the radius of that circle is going to be the value of x. So that's why the length of this rectangular prism is 2 pi and then xi, because that represents the value of x at that endpoint. So to find the volume of this rectangular prism, we've got 2 pi times the radius, which is our value of x at that endpoint. The width is going to be delta x. And then the height of that rectangular prism, that's this here, I'll do that in blue, that's going to be the height of the function evaluated at that endpoint. So this is just the formula for one cylindrical shell. Now, if we want to then add them all up, we can get an approximation for the volume so that we would have the sum is I from 1 to n. So let's say we split it up into 20 cylindrical shells. N would be 20. So we take all those cylindrical shells, find the volumes, and then add them up. Now, if we want to get the exact volume, we want to take the limit as n goes to infinity so that we can get more and more cylindrical shells. The widths get smaller and smaller, and we get a more the higher the value of n, the more accurate that volume is going to be. So to get the exact value, we're going to take the limit as n goes to infinity of the sum from 1 to n of 2 pi xi times f of xi, and then times your width, your change in x. Now, instead of doing the limit of all these Riemann sums, remember we can set this up as an integral, and when we do that, that's what we get down here. So this is how we're going to integrate using the idea of the cylindrical shells. We're going to do it on the interval from a to b, and we're going to write it as 2 pi x times f of x dx. And now remember, this is when we are rotating around the y-axis. So we have to make sure that we keep that in mind. With cylindrical shells, it's different. It's the opposite of the disk in the washer method. Okay, let's look at this first example. It says define R as the region bounded above by the curve f of x is equal to 1 over x and below by the x-axis, and we're going to do this over the interval from 1 to 3. Find the volume of the solid of revolution that's formed by revolving R around the y-axis. So if you look in this first picture, the region that we're going to revolve around the y-axis is this here that I'm highlighting in pink, and we're doing this from 1 to 3. Then when we spin it around the y-axis, that's the picture we're going to get in part B that shows the solid of revolution when we spin that region around the y-axis. So this is set up nicely for us to be able to use finding the volume by cylindrical shells. It's defined in terms of x, but we spun it around the y-axis, so we're going to use the formula that's up here in the box right above the problem. So to set this up, I'm going to find the volume by integrating on the interval from a to b, 2 pi x f of x dx. So we're going to plug in our interval as from 1 to 3. We have 2 pi x, and then the function is 1 over x, and then we have that as dx. When I clean that up, I can cancel those x's. I can get rid of this x, and x times 1 over x, that disappears, and it turns to 1. So now I'm integrating from 1 to 3, just the constant 2 pi. So now when I find the antiderivative, I'm going to have 2 pi x, and I'm going to evaluate that on the interval from 1 to 3. When I plug in 3 first, I'm going to get 6 pi. When I plug in 1, I'm going to get 2 pi. So when I subtract, I'm going to get a total of 4 pi, and that's going to be... So here's our second example of the method of cylindrical shells. It says define R as the region bounded above by the graph 2x minus x squared and below by the x-axis over the interval from 0 to 2. We're going to find the volume of solid of revolution formed by revolving the region around the y-axis. So when we look at this first picture, the region R is under the graph of 2x minus x squared and above the x-axis on the interval from 0 to 2. That's this here that I'm highlighting in pink. Then when we rotate it around the y-axis, this is the picture we're going to get. So we can visualize that. So since we're defining everything in terms of x, but we're rotating around the y-axis, we can go ahead and use the cylindrical shell method. So I'm going to use the formula that the volume is on the integral from a to b, 2 pi x times f of x dx. So I have the interval from 0 to 2. I'm going to take 2 pi x times f of x, which is 2x minus x squared dx. Now to simplify that, we're just going to multiply through by the x. I can pull the 2 pi out in front to make it less complicated. So I'm just going to distribute the x, and I get 2x squared minus x to the third dx. Now, let's find the antiderivative. When I take the antiderivative of 2x squared, I'm going to get 2x to the third over 3. When I take the antiderivative of minus x to the third, that's going to give me minus x to the fourth over 4. And I need to evaluate this from 0 to 2. So when I plug in 2 first, I get 2 times 2 cubed over 3 minus 2 to the fourth over 4. Then when I evaluate it at 0, I'm just going to get 0. So that disappears. When I finish evaluating this, you're going to get, let's see, 8 pi over 3, and that's going to be units cubed. So in this next example, we are going to use the cylindrical shell method, but now we're going to practice rotating the region around the x-axis. So because of that, we have to write everything in terms of y, and that includes our upper and lower bounds. So the problem reads, define Q as the region bounded on the right by the graph of g of y is equal to 2 square roots of y, and on the left by the y-axis for y is equal to 0 to 4. So now notice, instead of giving it on the x-axis, the interval is now on the y-axis in terms of y. So we're going from 0 to 4. Here's our region. We're going to find the volume of the solid of revolution formed by revolving Q around the x-axis. So now we're spinning it this way. And then this is the volume that it produces. Okay, so we're going to set up our volume formula. Now, in the formula, it's labeling it as C and D now instead of A and B, so that you recognize that this is going to be different. It's not on the x-axis. They use A and B for when your interval is on the x-axis, and C and D when your interval is on the y-axis. And so we have 2 pi. My radius now, instead of being x, it's going to be y. And we're going to write it in terms of our function g of y. That's going to be the height of our cylindrical shell. So now, since our interval is on the y-axis from 0 to 4, I'm going to write 0 here, 4 here, and then I have 2 pi y, and then my function in terms of y is 2 times the square root of y, and then we have dy. Now I want to point out that most of the time functions are given in terms of x, and we're lucky because this example has already translated everything for us in terms of y. If the function was given in terms of x, we would need to solve it for x and put it in terms of y in order to use this. But lucky for us, the book had set this up for us already. Okay, now when I clean this up, remember I can write the square root of y as y to the 1/2. So I'm going to rewrite this integral from 0 to 4 of 2 pi, and actually I can take this 2 here and this 2 here and multiply it to get 4. So I have 4 pi, and then I can take the y to the first times the y to the 1/2 and combine those together to get y to the 3/2. So now my integral is simplified, and then find the antiderivative of y to the 3/2. When I take the antiderivative of y to the 3/2, I have to add 1 to that, so that gives me y to the 5/2. And when I divide by 5/2, that's the same as multiplying by 2/5. And then I'm going to evaluate that on the interval from 0 to 4. When I plug in 4, I'm going to get 2 times 4 to the 5/2 over 5. When I plug in 0, I'm going to get 0. So when I work that out, I'm going to get 256 pi over 5. And of course, since that's volume, it's going to be units cubed. Now we can also rotate the region around horizontal and vertical lines other than the x and the y axis. So in this next example, we're going to take a look at that. Now, in this example here, we're going to rotate around the y-axis, so we need to have everything in terms of x. So what we're going to have to do is adjust the radius for that shift. So the problem reads, define R as the region bounded above by the graph of f of x is equal to x and below by the axis over the interval 1 to 2. Find the volume of the solid of revolution formed by revolving R around the line x is equal to -1. So remember, in general, trying to add up the volume of all those cylindrical shells. And the cylindrical shell, if we cut it and unwrap it, remember it's like a prism. And so our volume, when we set up our integral, is going to be 2 pi times the radius times the function. And we're going to do this on the interval from 1 to 2. So what we're going to have to do is adjust for the fact that the radius is not just x anymore because we shifted our center. We're revolving this around the line x equals -1. So if we imagine that the center is here at this pink dot and the radius comes out this way, it's the value of x plus 1 more, right? So if I come out this way, it's the value of x plus this extra unit right here that I'm drawing in green. So we're going to rewrite our integral for the volume as 1 to 2, 2 pi. The radius is now going to be x plus 1 because it doesn't start from the origin out for the value of x. It's shifted over 1. So it's going to be from -1 to 0 and then from 0 to x. So we're counting that extra unit. And now f of x is x. And then we have dx. So this is our new radius because we shifted over, and our new axis that we're spinning this around is x is equal to -1 rather than the y-axis. I'm going to simplify this. I can pull the 2 pi out in front. And when I multiply x times x plus 1, that's going to give me x squared plus x dx. And now when I find the antiderivative, that gives me x to the third over 3 plus x squared over 2, and we're going to evaluate that from 1 to 2. When I plug in 2, I'm going to get 8/3 plus 4/2, which is 2. And then I'm going to subtract what I get when I plug in 1, which is 1/3 plus 1/2. When I finish multiplying all that through, my final answer is going to be 23 pi over 3. And then, of course, because this is volume, this is going to be units cubed. Now, our next example, we're going to look at the volume of a solid of revolution for which that region that we spin around the y-axis is bounded by the graphs of 2 functions. When we look at this, it says, define R as the region bounded above by the graph of the function square root of x and below by the graph of the function 1 over x over the interval from 1 to 4. We're going to find the volume of the solid of revolution generated by revolving R around the y-axis. So because we're rotating this around the y-axis, we want everything in terms of x. So our interval is going to go from 1 to 4, and we have 2 pi x times the function f of x, and this represents the height of that cylindrical shell. Because the axis of revolution is the y-axis, the radius of the shell is just going to simply be x, right? It's from the center, from the y-axis out, it's going to be that value of x. That will be our radius. So we don't need to make any adjustments with that x for our radius. However, the height of the shell is going to be the difference in the functions. So the height of the shell is going to be f of x minus g of x. So that's what we need to put in for the height when we're taking that into consideration and setting up our integral. So we have the integral from 1 to 4. We have 2 pi x. That isn't going to change. But when we multiply that by the height of the cylindrical shell, we got to take f of x minus g of x because it's the difference between those two functions. Now, since f of x is the square root of x, we're going to put that in, and then we're going to subtract g of x, which is 1 over x dx. When I simplify my integral, I have 2 pi, and I can write that x here as x to the 1/2. So when I multiply it by the x on the outside of the parentheses, I get x to the 3/2. And then when I take x times 1 over x, I just get 1. I can pull that 2 pi out in front, and I have x to the 3/2 minus 1 dx. Now I'm ready to find the antiderivative. So the antiderivative of x to the 3/2 is x to the 5/2 divided by 5/2, which is same as multiplying by 2/5. And the antiderivative of 1 is x. And I'm going to evaluate that from 1 to 4. When I go and evaluate that, I'll let you guys do that to practice. Your final answer should be 94 pi over 5, and that's going to be units cubed. So now that we've studied several methods for finding the volume of a solid of revolution, we're now going to take a step back and look at the summary of everything that we learned. And a lot of times where students get confused is they're trying to figure out which is the best method to use. And a lot of times it comes down to a choice on which integral or which method is the easiest to evaluate, because more often than not, there's more than one way to do this. So a lot of times it's just comes down to experience and practicing and seeing which way is the easiest. And the book gives a really great chart that summarizes the different methods. And this chart that's given is specifically for rotating around the x-axis. And the book suggests that the student make their own chart just like this with all the methods for finding a volume of solid around the y-axis, which I think is a really good exercise. So these are all the methods for revolving around the x-axis. You should try to create your own chart just like this in order to step back and summarize what you've learned. So in the last couple of examples, we're going to walk through on practicing determining which is the easiest method. Now that's not to say there isn't more than one method, but this is more of a discussion on let's take a look at what the possibilities are and consider what's the easiest method. Now, using the chart above, they want you to consider the region around the x-axis while working on parts A and B of this problem. So in part A, it says the region is bounded by the graphs y equals x, y equals 2 minus x, and the x-axis. And then, so part A shows the region that's going to get rotated, and then in graph B, it shows what it looks like once it's rotated. So when we look at that region in graph A, since we want to integrate it with respect to x, if we're using the disk method, we would have to break the integral up into two pieces because we have two different functions bounding the region over the interval from 0 to 1 and then the interval from 0 to 2. So taking a look at this, on the interval from 0 to 1, we have y equals x as the upper function. And then looking at the interval from 1 to 2 in purple, we have a different function, which is 2 minus x as the upper function. So although we could do it using the disk method, we would have to use two integrals. Using the disk method, we would set up the integral for the interval from 0 to 1. We would have pi. Now, using the disk method, remember you're thinking about taking a cross section, and when you do that, it's going to look like a circle, and then you integrate that to get the volume. So the radius of that disk would be x, because on that first interval, the radius would come out from the x-axis to the line y equals x. And then we square it. This would be my r. So we have pi r squared. And then we would have to have a second integral from 1 to 2. And we would do the same thing. I would have pi r squared, but my r would be the function, so 2 minus x, and I would square this. So although this would work, there's a little bit more to it because we would have to evaluate two different integrals. Now, if we use the shell method, we would use the functions of y to represent the curves. So we could rewrite, because this is revolving around the x-axis, we would make sure that we have everything with respect to y. So this function, y equals 2 minus x, would be rewritten as x is equal to 2 minus y. And then we could write it all in terms of one integral using the shell method. So then writing my integral, I would have 0 to 1, and I changed my interval from 0 to 2 to 0 to 1 because remember we're doing this with respect to y, and I've got to do this on the y-axis from 0 to 1. So when I write my formula for the cylindrical shells, I'm going to have 2 pi, my radius is going to be y, and then the height of my shell is going to be the difference between those two functions. So I have 2 minus y, and I'm going to subtract y. And then I have dy. Now when I simplify that, I'm going to get 2 pi y, and then inside the parentheses, I can simplify the height of that shell as 2 minus 2y dy. So using the cylindrical shells, we would only have to find and evaluate one integral, versus with the disk method, we would have to do two. Now you should get the same answer no matter which one you use, but me personally, I think the cylindrical shell method would be easier. Now in part B, we need to find the region bounded by the graphs of y equals 4x minus x squared and the x-axis, and then rotate it around the x-axis. So in the picture labeled A, you see our region. And then in the picture B, you can see if we rotate it around the x-axis, we get this picture in graph B. Now, if I look at this, and I imagine cylindrical shells for this, it would be really difficult to come up with the height of that cylindrical shell because we have the same function on either side of that cylindrical shell. So typically when we find the height of the cylindrical shell, it's just going to be one function, or you take the difference between two functions. But when it's bounded on both sides, to take and find this difference from here to here, how do we take the same function and subtract it from itself to find that height? So I think that's going to be a little too difficult to use cylindrical shells. So going with the disk method, remember to find the volume using the disk method, we would choose our interval, in this case it's 0 to 4. And we're trying to find the area of that cross section, which is the shape of a disk. So we have from 0 to 4 pi r squared dx, and then our radius of the disk is just going to be the value of the function. So really all we have to do is integrate from 0 to 4 pi, and then our radius is 4x minus x squared. I square that because this is our radius inside the parentheses, and then this would be fairly simple to integrate, so I think using the disk method would be the best here.